Hi. So today we'll be talking about black body radiation. Okay. Black body radiation. In this session, we'll talk about black body radiation first. Then we'll be covering some topics about how to apply this theory of black body radiation to black holes. And finally, I will be ending with a problem of n number of oscillators coupled in a one-dimensional chain. Okay. Now, this problem of n-coupled oscillators, it's an interdisciplinary problem. It appears in a number of fields of physics and also in other kinds of sciences as well. So that's what I'm going to end with today. Okay. So I'll start sharing my screen. Yes. Okay. So what is blackbody radiation? Before that, what is radiation? Radiation is something which propagates through space in the absence of any medium. Like you have heat waves, which are infrared radiations, lights, which is like in the visible spectrum, then you have ultraviolet radiation, and so on and so forth. Okay. And an important thing is that a radiation is actually the product of an oscillation in the medium. So there are fluctuations in the medium, and the radiation is a byproduct of this fluctuation. It's the energy emitted as a result of these fluctuations. Okay. So, so since radiation I have mentioned is caused by vibrations or fluctuations, you can say that there can be vibrations in many kinds of objects. For example, in solids there are vibrations, in liquids also there are vibrations, and in vacuum also there is vibrations. In solids, the particles which are responsible for vibrations in solids are phonons. So they are the ones which are responsible for the propagation of the vibration through the solids. Similarly for liquids as well. However, in vacuum, you don't have any molecules, right? So phonons cannot propagate vibrations through vacuum because in the absence of the medium, it won't do so. So what are responsible for causing vibrations in vacuums? Well, that is vibrations in vacuum can occur because of electromagnetic field fluctuations. So fluctuations in electromagnetic field, as you know, can give rise to radiations. So this is what I just explained. So radiations are given rise as a result of these vibrations or fluctuations of the electromagnetic field. And the mediating particle for this radiation are photons. So photons are basically the particles which carry this radiation. For example, you have visible photons, you have infrared photons and UV photons, and so on. Okay. So in order to study the vibrations of the electromagnetic field, one needs to know about the normal modes of an EM wave. Okay, so if I have a string vibrating, a string can have a different number of natural frequencies depending on how it is positioned at its two ends, right? So these various natural frequencies give rise to various normal modes of a vibrating string. So for any oscillating system in general, it can have a number of normal modes depending upon the number of natural frequencies it has. So the normal modes of an electromagnetic wave, if I consider an vibrating electromagnetic field, then the normal modes of that vibrating electromagnetic field can be quantified by two quantities. One is the wave number of the EM wave which propagates as a result of that vibration, and the other is the modes of polarization of the electromagnetic wave. Okay. Now, since in vacuum, divergence of the electric field is equal to zero, so there can be only two modes of polarization, and we denote the modes of polarization by alpha and the wave number by k. So once we know the wave number and the modes of polarization, then we can actually write the Hamiltonian for the vibrating electromagnetic fields. But there is one thing we need to know before we are able to write the Hamiltonian by, because if you recall the example of a simple harmonic oscillator, then its Hamiltonian has two parts. One is the kinetic energy and the other is the potential energy. Okay, so the kinetic energy simply comes from the velocity of the oscillator itself, and the potential energy comes because it is in a trapped harmonic potential, right? And it depends upon the coupling constant. If it's a spring, it depends upon the coupling of the spring, and so on. And it can be written in terms of the angular frequency of oscillation, right? So if I have an electromagnetic wave here, and I'm given its wave number and its propagation speed, then the angular frequency of the electromagnetic wave can be related to the wave number and the the speed of the electromagnetic wave by a dispersion relation, right? So different waves can have different dispersion relations in general. And for an electromagnetic wave, this is a dispersion relation. So omega equal to ck. This, I guess, is well known because this is the dispersion relation of an electromagnetic wave in vacuum. C is the velocity of the wave in vacuum. In this case, I can consider it to be a light as well because light is an EM wave. So this is the dispersion relation which I get. So now once I have the omega, if and now I can write the Hamiltonian of the EM wave as a sum of the individual energies of each harmonic oscillators, where the angular frequency of each oscillator is given by this omega alpha k. So the angular frequency depends upon the state of polarization as well as the wave vector. Okay. And so if this is my angular frequency, then I write the Hamiltonian as half into summation over all k and alpha, p k alpha square. This is the momentum of associated with each photon, plus omega alpha square, u k alpha square. U is the position coordinate and omega is the angular frequency, and which I get from this relation. Okay. Now, in order to formulate the partition function, free energy, pressure, and all these quantities, I need to define boundary conditions. So where am I working? So let us consider that my radiation is trapped in a cubic box of side L, such that the volume of the box is L cube. And suppose there are periodic boundary conditions. Now, why do I use periodic boundary conditions? This will come to light in a short time because basically I'm working with Fourier modes. That is why since I'm using periodic boundary conditions, I will be able to work with Fourier modes. So that is why I consider this to be a periodic box. Okay. And what are Fourier modes? Fourier modes are basically the amplitudes. The when you represent a vector in the Fourier basis, then you write it in terms of sines and cosines. And since sines and cosines themselves are periodic functions, so if I'm working with a periodic real space domain, then it becomes easier for me to express it in terms of the Fourier basis. Okay. So if I have a periodic box of side L, then these are the allowed wave numbers which I have. K is equal to 2 pi. Um, some it can be nx squared plus ny squared plus nz squared or anything. So it is a function of these quantities where nx, ny, nz are the integers, and they can take any value from 0 to infinity. Now you will find that since nx, ny, and nz can take values from 0 to infinity, and there is no restriction on the values of k. So what can happen is that since there is no restriction on value of k, k can go to infinity. All right. So I can have infinite number of Fourier modes here. Now, if I associate it as equal amount of energy to every Fourier mode, then what happens is that I have extremely high energy stored in the large k modes. Why? Because of this. Over here, omega is equal to ck, right? So if I have some energy in the high Fourier mode, then you see that as k goes to infinity, this energy will also go to infinity, right? So that is why this leads to a blow up of energy in the high k modes in the classical formulation. So if I use this classical Hamiltonian, then you will find that the internal energy and everything which I calculate will blow up in the large k modes. And this is known as the ultraviolet catastrophe. So what is the resolution to this ultraviolet catastrophe? The resolution is that instead of using a classical formalism, I need to use the quantum definition, quantum Hamiltonian for these photons. That is, we assume that the electromagnetic energy is quantized as per the Hamiltonian, which is given over here. So this is the quantum Hamiltonian, Q denoting quantum, summation over h cross ck n alpha k plus half. So you see, this is basically the Hamiltonian of a quantum harmonic oscillator having angular frequency omega equal to ck. So h cross omega n plus half. So this is that Hamiltonian. Okay, where n can take integer values like 0, 1, 2, 3. So using this Hamiltonian, I can ask what is my internal energy. Before the internal energy, another important thing which one must ask is what is the partition function of this system. So since we consider the oscillators to be independent of each other, there are no interactions between photons. Okay. So then the partition function is nothing but a summation over all possible arrangements of n alpha k e to the power minus beta h cube. Okay, so this can be decomposed as a product and a summation. So this is a product over a given wave number and alpha and the number of occupancy number for that alpha and k. And the summation is over exponential of minus beta h cross k in alpha half plus half. Okay, so if I do the summation while keeping this product term aside, if I do the summation over the occupation numbers n alpha, that is, yeah, if I do is, sorry, the energy levels, if I do a summation over the energy levels n alpha, then what I get is that I have an infinite GP. So I take the e to the power minus beta h cross ck by 2 outside, and then it turns out to be a summation over this quantity. So then Z alpha turns out to be product over k comma alpha e to the power minus beta h cross ck by 2 divided by 1 minus e to the power minus beta h cross ck. So this is my partition function for blackbody radiation, which I have modeled as a sum of a number of quantum harmonic oscillators. So then I ask, what is my internal energy? So the internal energy is basically an expectation of the Hamiltonian. And if I look at this thing, the expectation of Hamiltonian is nothing but the expectation of the over this quantity n alpha. So you can written as summation over k alpha h cross ck expectation n alpha plus summation over k alpha h cross ck by 2. Okay. Now what is the average of n alpha? So the average of n alpha can be written as in this form summation of n going to 0 to infinity n e to the power minus beta h cross ck n plus half divided by n going from 0 to infinity e to the power minus beta h cross ck n plus half. So basically the sum over all probabilities, and this is the weighted sum over the probabilities, the weight being n. Okay. So I can, since this half Walla term does not depend on n, I can take this out of the numerator and I can take this half term out of the denominator. So the expectation turns out to be this quantity, summation n equal to 0 to infinity n e to the power minus beta h cross ck by summation e to the power minus beta h cross ck. Okay, n. Yeah. So this summation can be written in form of a derivative of a logarithm. So this comes from this. All right. And inside the logarithm, you have this summation from n of n going from 0 to infinity. So if I do this summation now, then basically it turns out to be 1 by 1 minus e to the power minus beta h cross ck. And then I take the derivative and the occupation number expectation turns out to be e to the power minus beta h cross ck divided by 1 minus e to the power minus beta h cross ck. So I plug this into the expression of u which I had over here. Then u turns out to be summation k alpha h cross ck half plus e to the power minus beta h cross ck by 1 minus beta h cross ck. Now this is in terms of a discrete number of oscillators. What if I have an infinite number of them? What if it's a continuous system as radiation is? Then I convert the summation into an integral. So this is similar to what has been done in the previous classes as well. You would note that there is an extra factor of 2 which comes over here. This 2 comes because there are two modes of polarization. So alpha can have two values basically. That is why there is a factor of 2 over here. Okay. So then the summation first term, what does the first term become? First term becomes v by 2 pi whole cube integration ck d3k. And I write this as v into e naught, where e naught given by c by 2 pi whole cube integration k d3k is the 0 point energy. Okay, so since k can go from 0 to infinity, the 0 point energy is actually an infinite quantity. But since we are concerned with energy differences, because 0 point energy only happens when there is no energy. That is what is known as 0 point energy. There is no excitation. However, photons are always excited. You can't have a photon which is unexcited, right? Because then the speed of a photon becomes zero, which is unfeasible. All right. So since photons are always excited quantities, so we are not bothered with the 0 point energy at all. What we look at is the energy of excitation, which is this second quantity over here. So what does the second quantity become? The second quantity ends up becoming 2v by 2 pi whole cube integration d3k h cross ck divided by e to the power beta h cross ck minus 1. So I write this d3k as 4 pi k square dk using the condition of spherical symmetry. Okay, so then the integral turns out to be integration 0 to infinity dk h cross ck cube divided by e to the power beta h cross ck minus 1. Now I put x equal to beta h cross ck. Then dk is dx by beta h cross c and k is equal to x by beta h cross c. If I make the substitution, then this is what my excitation energy turns out to be. Okay, so the excitation energy per unit volume, that is E star by V, is equal to h cross c by pi square kVt by h cross whole to the power 4 into this integral, that is integration 0 to infinity dx x cubed by e to the power x minus 1. Now, if you remember our class on Bose-Einstein condensation, we had a similar integral which could be written in terms of a gamma function and the Riemann zeta function. So this integral is nothing but gamma 4 into zeta 4. Gamma 4 is equal to 6 and zeta 4 is pi by pi to the power 4 by 90. So this thing becomes equal to pi to the power 4 by 15. Therefore, the excitation energy per unit volume is equal to pi square by 15 kBt by h cross whole cube into kBt. Okay, so this is the expression for the excitation energy of blackbody radiation. As you can see, it depends upon the speed of the radiation, speed of the photons, that is c, and the temperature of the radiation, that is capital T over here. Okay, so hotter the box, the higher would be the energy per excitation energy per unit volume. At T equal to 0, it's not excited at all. Okay, so once we have the excitation energy, and since my radiation is trapped in a box, then I can think of this radiation to be as a photon gas, where each particle of, like I had the ideal gas before, where the gas was composed of molecules. Here, the gas is composed of photons. So photons are like individual particles of the gas. And therefore, since in case of the ideal gas, we had it exerting some pressure on the walls of the container, here also the radiation will exert pressure on the walls of the container, which is known as radiation pressure. And we calculate this pressure in terms of the pressure exerted by the photons on the walls. Okay, so what is the free energy of a photon gas? The free energy is given by F equal to minus kBt ln Z. I have calculated ln Z, I calculated Z over here, right? So Z was this quantity. If I take a log of this, then the product becomes a summation. And then I have F equal to kBt summation k alpha beta h cross ck by 2 plus log of 1 minus e to the power minus beta h cross ck. Again, I replace the summation by an integral. So I replace summation by 2 phi by 2 pi whole cube integration d3k. And then this is what my free energy turns out to be. So once I know my free energy, I can calculate the pressure as the derivative of the free energy with respect to volume at a constant temperature. So the pressure of the photon gas is given by minus del F del V at constant T. If I do the integration, then you will see there is no volume term inside the integral. The only volume term is outside. So this becomes minus integral d3k by 2 pi cube h cross ck plus 2 kBt ln 1 minus e to the power minus beta h cross ck. So I again separate this out into two terms. One is the temperature independent term and the other is the temperature dependent term. The temperature independent term is the 0 point pressure, which is P0. And this is the temperature dependent term, which comes from the radiation. Okay, so what is this quantity then? Uh, so what is this quantity? I can write this quantity. So then basically D3K can be written as 4 pi k square dk. Okay, so that's why I have k square ln 1 minus e to the power minus beta h cross ck dk. So if I integrate this quantity by parts, then I basically integrate over k cube and differentiate the logarithm. Then the quantity involving the integration over k cube becomes 0 because of the limits of the integral over here. And then I have this to be integration from 0 to infinity dk k cube by 3 beta h cross c e to the power minus beta h cross ck by 1 minus e to the power minus beta h cross ck. Okay, so this is what the pressure due to the excitation turns out to be. I can further simplify the quantity and I get this expression for the excitation pressure. Now I had seen earlier that the excitation energy was given by E star, which is of this form. So if I compare this expression with this expression, I will see that the excitation pressure, extra pressure, is nothing but 1/3 E star by V. So this is the radiation pressure, which is given as a result of the radiation. So this is a 0 point pressure, and this is the pressure which comes because of the excitation. Okay, and this differences in the radiation pressure on two sides of boundary can result in Casimir forces, which can be measured easily in the laboratory. Now, you will note one thing over here that we had also obtained a similar expression for pressure in terms of energy and the volume for the ideal gas we had done earlier, and also for the relativistic ideal gases as well. So for a relativistic ideal gas, we had the energy scaling as mod p to the power of s, where s could be equal to anything. S was chosen to be equal to 1 for a relativistic particle, right? And the pressure was given by S by D into E by V. So this is the pressure of a boson gas of a d-dimensional ideal gas in d dimensions. Okay. So if I put S equal to 1 and D equal to 3, I get that this expression. So that is one analogy which we can draw with what we had learned earlier. Okay. So what can happen as a result of the pressure? So since the radiation is exerting pressure from inside on the walls of the container, if I make a hole in the wall, then what happens is that radiation comes out of this hole. So basically, if I have a light source in a box and if the box was completely opaque, then the light would not come out. But uh, what one must note that is that the light radiation, it exerts a pressure on the box. And if you make a hole in the box, then the light comes out of that box, right? So this is because of radiation pressure that the light comes out of it. And this way in which the light comes out, this can be written uh, in terms of Stefan Boltzmann's law. So what is that law and how can we derive that law from what we have learned earlier? Okay. So if there is a hole in the container wall, then the photons can escape from it. Then the number of photons which come out per unit area. Okay, number of photons which come out, the energy flux per unit area per unit time is given by phi, which is equal to expectation of C perpendicular into E by V. So this is the energy per unit volume, and this is the energy per unit area per unit time coming out of this box. So C perpendicular is the component of the velocity of the photons which are perpendicular to this wall, that is perpendicular to this hole. So how can we calculate C perpendicular? We can calculate it in the following manner. This is equal to 1 by 4 pi integration 0 to pi by 2 2 pi sine theta d theta c cos theta. How do we get this quantity? So this is basically the solid angle which I integrate. I mean, in spherical if I consider spherical coordinates for a and the r value, that is the so in spherical coordinates, the volume element is basically a r square sine theta d theta d phi dr, right? So if I have a so then the area element on the spherical surface is given by r sine theta d phi, right? So over here, the r is basically the c cos theta term, which is the component of the velocity along this direction. That is r, and I basically integrate over 5 the azimuthal coordinate, and then I do the integration over theta from 0 to pi by 2. And I have this factor of 1 by 4 pi outside because that is the total solid angle of a spherical surface. Okay, so this is the basically the uh, what is expectation of C perpendicular. Okay. So if I calculate this, this turns out to be equal to C by 4. So therefore, phi is equal to C E by 4 times volume. And if I replace the expression for E, which I had over here, that is the excitation energy, then phi turns out to be equal to pi square by 60 kb to the power 4 divided by h cross cube c square into t to the power 4, which is equal to sigma t to the power 4. So this is the Stephens-Boltzmann law for blackbody radiation. What does this law state? That the energy flux per unit area per unit time coming out of a black body is proportional to the fourth power of the temperature. And the proportionality constant is known as the Stephen-Boltzmann constant, which is given over here. So sigma is equal to 5.67 10 to the power minus 8 watt per meter square Kelvin to the power of minus 4. This is known as Stephen's constant. Now, what is the implication of considering the quantum treatment of photons rather than classical? So we had mentioned earlier that if I treat the photons as classical quantities, then since k is unbounded, then we can have infinite energy in the high k modes, right? So this was known as the ultraviolet catastrophe. So now let's see how our treatment avoids the ultraviolet catastrophe. So let us say that the excitation energy per unit volume can be written as integral dk epsilon k comma t, where epsilon is this quantity, right? So I had a P star by written like this in this manner. Okay, so basically from this I can get that epsilon is equal to h cross c by pi cube k cube divided by e to the power beta h cross ck minus 1. So this is basically the energy density in the wave vector k, energy per unit volume contained in a wave vector k. Okay, so what is the flux of radiation emitted by the wavelengths which lie in the interval k to k plus dk? So what is the flux of radiation emitted by these modes of radiation? Okay, so then that flux is given by I as a function of k comma t, which is c epsilon by 4. Why c epsilon by 4? This comes from the Stephens law itself. C epsilon by 4. So we had a phi equal to c by 4v. So E by V is basically epsilon. Therefore, I kt is equal to c by 4 epsilon. Okay. So this is equal to h cross c square by 4 pi square k cube by e to the power beta h cross ck minus 1. So this is the spectrum of the flux of radiation emitted by the black body. Right. So let us take a look at how this spectrum looks like. So the ultraviolet catastrophe had predicted that the spectrum would go to diverge to infinity for high K. So let us see whether that happens now or not. So this energy spectrum, it peaks at k cube by e to the power beta h cross ck minus 1. Why? It peaks at a value of k equal to k star y, because k cube by e to the power beta h cross ck minus 1 peaks at k equal to k star. What is the small k behavior of this quantity? At small values of k, I can Taylor expand the exponential. So this quantity becomes equal to beta h cross k, and therefore this scales as kBt by h cross c into k square. So you see the ik is proportional to k square at small k, and at large k, that is k much greater than the k star. What happens is that I can drop this exponential becomes much larger than 1, and this is basically e to the power minus beta h cross ck. So you see that at large k, the spectrum falls off exponentially, and at small k, it rises as a parabola. So this is the energy spectrum I get. In the small k part, it's a parabola, and in the large k part, it falls off exponentially with k. So you see the ultraviolet catastrophe is avoided in this situation. Earlier in the classical situation, it would have gone off like this into infinity, but because of the quantum treatment of photons, the quantum treatment of radiation, to be precise, the ultraviolet catastrophe is avoided. So this is what the energy spectrum of a black body radiation looks like. So this completes the derivation of black body radiation. Okay. So let us take a look at the application of blackbody radiation to black hole thermodynamics. So what is this thing? So according to Bekenstein and Hawking, the entropy of a black hole is proportional to its area, and it is given by S equal to kbcq divided by 4gh cross A, where A is the surface area of the black hole, c is the speed of light, kb is Boltzmann constant, g is the acceleration due to gravity, and h cross is the Planck's constant. First question is calculate the escape velocity at a radius r from a mass m using classical mechanics. Using this, find the relationship between the radius of and the mass of a black hole by setting this escape velocity to the speed of light. Why? Because escape velocity is the minimum amount of velocity that is required to escape out of a central potential, right? Escape from a central force. Earth has a escape velocity, Jupiter has a escape velocity, Sun, and different objects have different escape velocities. In general, different central forces can have different escape velocities. Okay. And why is this a black hole? Because a black hole is something because light cannot escape from it. That is why if I calculate the escape velocity of a sphere of radius r of mass m, I assume the black hole to be spherical. And if I calculate the escape velocity at a radius r from a sphere of mass m, then uh, what you will see that if I put this escape velocity in equal to light, I get a relation for the radius and the mass of a black hole. So that is what we'll be doing here. So for a mass m at a distance r, the gravitational force is given by g capital M small m by r, where small m is the mass which is placed at a distance capital R from the center of this central force. Okay, and this is equal to the kinetic, and if I set the potential energy, this is the gravitational potential energy which that mass small m feels, and the kinetic energy of the mass small m is given by mve square by 2, where VE is the escape velocity. So if kinetic energy is less than the potential energy, it does not escape. If the kinetic energy exceeds the potential energy, it can escape. So this is known as the escape velocity, the point at which the kinetic and the potential energy becomes equal. So I calculate VE as root over 2gm by r. So if I set VE equal to c, then I obtain r is equal to 2g by c square into m. So this is the radius of a black hole in some sense, because I am setting the escape velocity to the speed of light. Okay, and as you can see, the radius of the black hole is linearly dependent on the mass of the black hole. So for a mass larger than this given ratio, nothing will escape from the distances which are closer than r. Okay, so if I'm standing at a if I'm emitting light from a distance which is closer than r, then the light won't be able to escape the black hole. So this is what this expression says. So this is the expression for the radius of a black hole, r equal to 2gm by c square. Now, does entropy increase or decrease when two black holes collapse into one? And what is the entropy change for the universe when two solar mass black holes coalesce with each other? So, suppose I consider two identical black holes. They both have the same entropy S1. So initial entropy of the system was S1 plus S1, that is 2S1, and the final entropy is S2. So therefore, the change in entropy is S2 minus S2S1. Now, what is the expression for entropy which I had earlier? This is the expression for entropy, kbc cube by 4gh cross into A. So S is dependent on A only. Therefore, this becomes kbc cube by 4gh cross A2 minus 2A1. And you know that the curved surface area of a sphere is basically 4 pi r square. Therefore, A2 is 4 pi r2 square, A1 is 4 pi r1 square, and this is what I get after substitution. I had calculated r over here as 2gm by c square, right? So I put over here instead of, so here is the substitution which I make. So after colliding with each other, the mass of the new black hole is basically 2 times m. So therefore there is 2g into 2m by c square whole square. And this is r1, which is 2g by c square into m itself. So if I calculate this quantity, it turns out to be 8 pi gkb m square by ch cross. which is greater than 0. Therefore, the merging of two black holes increases the entropy of the universe. And what is the increase in entropy? The increase in entropy is proportional to the mass of black hole which are colliding. Okay, so in this case, both the masses of both black holes were equal. If they were unequal, then this would have a different dependence on the mass. But at the end of the day, it depends upon the mass of the new black hole and the mass of the earlier black holes which had collapsed together. Okay. So now let us consider the collapse of two solar mass black holes and see what order of magnitude this entropy can become. So solar mass is basically 2 into 10 to the power 30 kg. And if I substitute that expression over here, then delta S turns out to be 3 into 10 to the power 54 joule per Kelvin. That's quite a large quantity. Okay, so it increases by a huge amount. And I can also calculate for this entropy is basically the information entropy. Okay, so when two black holes collide, some information is lost in the form of radiation. That is basically Hawking's radiation. When black holes evaporate, they lose information. This information comes out of in a scrambled quantity, and that is the Hawking radiation. So, what is the information that is lost on the collapse of two black holes? So in units of bits, this information is so if you remember the definition of information entropy, S is equal to KBL into. So from that I get n KBL into, where n is the number of bits of information which are there. From that I get n is equal to delta S ln2 by KB. So this much amount of information is lost on the collapse of black holes, and this is in units of bits. So now the internal energy of the black hole is given by the Einstein relation E equal to mc square. What is the temperature of the black hole in terms of its mass? Alright, so for this purpose, we use the thermodynamic definition of temperature. That is 1 by T is equal to del S by del E. And I had already calculated the entropy of a black hole earlier. Okay, sorry, the entropy of the black hole was given to me as kBc cubed by 4 pi gh cross into A. So what is the temperature of, and I E is basically mc square. So this becomes a derivative with respect to m. If the mass of the black hole is capital M, so this is the temperature of the black hole. So black hole temperature is equal to h cross c cube by 8 pi kbg into 1 by m. So it is inversely proportional to m. Now, a black hole actually emits thermal radiation due to pair creation processes on its event horizon. What are pair creation processes? You know, due to vacuum fluctuations, quantum vacuum fluctuations, particles can be created in particle-antiparticle pairs. Okay, they're constantly created and destroyed. So particle-antiparticle pairs are created, then they annihilate each other, get destroyed. Again, they can get created, and then again they annihilate, and so on. So this can happen due to vacuum fluctuations. Now, near the boundary of a black hole, what happens is that one of the two members of a particle-antiparticle pair which gets created due to vacuum fluctuations, it can fall into the black hole while the other escapes from it. This happens exactly at the fluctuations at the horizon of the black hole. Okay, so this is one of the arguments which are given for the emission of radiation from black holes. So these particles which escape from black holes, they are the ones which make up that radiation. Okay, so it is given to me that the black hole, suppose I assume that the black hole emits radiation because of these pair creation processes at the horizon, then find the energy lost due to such radiation. So the decrease in energy of the now if I treat the black hole as a black body of area A at a temperature T, then I can use the Stefan-Boltzmann's law to find the rate of energy lost due to such radiation. So what does Stefan-Boltzmann law state? It states that the energy flux per unit area per unit time is given by sigma T to the power 4. So energy flux per unit time is basically d del E by del T, where E is the energy per unit volume. And sorry, yeah, that is del E by del T. And per unit area, that's why I have the 1 by A factor over here. So 1 by A del E by del T is equal to minus sigma T to the power 4. The minus sign because this derivative is negative. Energy is getting lost. That's why. So if I use this formula, I can calculate the rate of energy loss due to such radiation. And as you will see, it is proportional to the temperature of the black hole and the area of the black hole as well. So the next question is that what is the amount of time it takes for an isolated black hole to evaporate, and how long is this time for a black hole of solar mass? So in order to answer this question, I take a look at this expression over here. Okay, so area A is equal to 4 pi r square, which is 16 pi g square by c to the power 4 into n square. E is mc square and T is given by this quantity. So basically I have ddt of mc square is equal to sigma T to the power 4 into area, right? So this is sigma, this is area, and this is T to the power 4. This implies that m square dm dt is equal to this particular quantity. So I get a differential equation which describes how fast the mass of the black hole decreases with time. So how fast the mass of an isolated black hole decreases with time. If I solve this differential equation, I get a solution of this form. Mt is equal to m0 cube minus 3bt whole to the power 1 by 3, where b is basically this constant h cross c to the power 4 by 15360 g square. This 15360 factor can be obtained by evaluating the numerics correctly. So this is the expression for the mass of the black hole at time t, while this is the initial mass of the black hole. So you see the black hole will evaporate once this quantity becomes equal to 0. So the time taken for the black hole to evaporate is given by T equal to m naught cube by 3b. Okay, so this is the time taken for an isolated black hole to evaporate, and it depends upon the initial mass of the black hole. So if I put so if I put m naught equal to 1 solar mass, then I get the time taken for an isolated black hole of 1 solar mass to evaporate. And this is equal to 2.2 into 10 to the power 74 seconds, which is considerably longer than the current age of the universe. And the current age of the universe is of the order of 10 to the power 18 seconds. Okay. Now, what is the mass of the black hole, which is in thermal equilibrium with the current cosmic background radiation at T equal to 2.7 Kelvin? So I had a relation between the temperature and the mass of the black hole earlier. We had calculated the temperature. By inverting that relation, I can calculate m is equal to h cross c cube by 8 pi kBt into gt. So if I put T equal to 2.7 Kelvin, I obtain the mass of the black hole, which is in thermal equilibrium with the current cosmic background. So this will be the mass of the black hole. Now consider a spherical volume of radius r. According to the recently formulated holographic principle, there is a maximum to the amount of entropy that this volume of space can have, independent of its contents. What is this maximal entropy? Okay, so this is something interesting. So we know that the entropy is an extensive quantity, right? So it depends upon the amount of mass which is contained within the volume. So for example, for the ideal gas, we had the entropy to be proportional to n, where n was the number of particles of the ideal gas I had. But here, according to the recently formulated holographic principle, there is a maximum to the amount of entropy that a volume of space can have, independent of its contents. So it is independent of n. So what is this maximal entropy? So the mass inside the sphere of R must be less than the mass that would make a black hole fill this volume, right? Because it could not be greater. Because if the black hole entirely fills this volume, the entire mass would be contained within that vacuum, and it would basically collapse to the singularity. So the mass inside the spherical volume of radius R should always be less than the mass that would make a black hole fill the entire volume. So if I bring in additional mass from infinity inside, so now let us suppose that I bring in additional mass from infinity inside the volume so as to make a volume filling black hole. So then the entropy will increase in the process, right? And then the final entropy will be the entropy of the black hole, which fills up this entire volume. So this is given by SPH, which is equal to KBC cube by 4GH cross into A. So the entropy should always be less than this entropy, which is the entropy of the black hole, which is the size of radius r, right? So this is a surprising observation on the upper bound of the entropy. That so this is the upper bound on the entropy because you can't have any more mass coming in over here, because the total mass should be equal, should maximum of the total mass should be given by the volume of the black hole of this radius r. Okay. The surprising observation is the upper bound on the entropy is proportional to area. Right. So here the entropy is actually proportional to area, whereas earlier we would expect the entropy to be proportional to n. This should also remain valid at even very high temperatures where interactions are unimportant. Okay. So what this holographic principle essentially states is that it appears that as if the degrees of freedom are living on the surface of the system rather than its volume. So earlier, the degrees of freedom of an ideal gas were given by its constituent particles, which could roam over the entire volume, right? So that is why each particle had 6 degrees of freedom. So if I had n particles, I had 6n number of degrees of freedom. On the other hand, in this case, the holographic principle states that the degrees of freedom reside on the surface rather than its volume. And it was formulated actually in the context of string theory, which attempts to construct a consistent theory of quantum gravity, which replaces particles as degrees of freedom with strings. Okay, so this is consistent with the derivations of string theory. Okay, so that brings us to a conclusion about black hole thermodynamics. Now coming to the last problem which I was speaking about, that is a one-dimensional chain. So suppose I have a chain of n plus 1 particles, each having a mass m. So there are n plus 1 particles, and I have n number of massless springs of spring constants k and relaxed length a connecting these particles. Now, the first and the last particles are held fixed at the equilibrium separation of Na. So basically, suppose I have two walls. The walls are separated by a distance Na. On the walls, there are two fixed particles out of these n plus 1 particles. So there are n minus 1 particles which are in between the walls, and all particles are connected to each other, their nearest neighbors, by springs. Okay, so I have a one-dimensional chain of particles such that the end particles are at the walls and they are fixed. Okay, and small a is the relaxed length of the string. So since the end particles of the at the walls are fixed, their displacements are zero. So if I denote the displacement of the ith particle by ui, then u0 and un are 0, since the endpoints are fixed. So then the Hamilton, which governs the motion of this string of particles, is given by this thing, where pi is the momentum of the ith particle and ui is the position coordinate of the ith particle. So the Hamiltonian is given by as a summation over I equal to 1 to n minus 1 pi square by 2m. Why I 1 to n minus 1? Because these are the ones which are moving. P0 and Pn are equal to 0 because they are static particles. Okay, so that is why H is summation I equal to 1 to n minus 1 pi square by 2m. This is the kinetic energy and this is the potential energy. So for potential energy, I have k by 2. K is the spring constant. U1 square plus summation I equal to 1 to n minus 2 ui I plus 1 minus ui whole square plus un minus 1 whole square. Why this form? Because u1 is only connected to the particle which is at 0. So basically it would actually, if I would write the summation, I should actually write k by 2 summation I going from 0 to n plus 1, sorry, I going from, yes, I going from 0 to n of this quantity, right? But since the nth particle is fixed and the 0th particle is fixed, so u1 minus u0, u0 is I assume to be equal to 0. So that is why I have u1 square over here. Plus you have terms like u2 minus u1 whole square plus u3 minus u2 whole square plus u4 minus u3 whole square and so on. These are the in between terms over here. Finally, you have um, un square minus un minus 1 whole square. And since un is also equal to 0, so this becomes un minus 1 square. So this is why the potential energy is written in this form. Now, using appropriate Fourier transforms, we have to find the normal modes and the corresponding frequencies. Okay, so what are normal modes? So you see, if you have a system of coupled oscillators, the normal modes are those modes in which all oscillators oscillate with the same phase. So those are known as the normal modes of the system. And what are the frequencies of the normal modes? The frequencies of the normal modes are the natural frequencies of the system. So clearly you see that if you have n number of coupled oscillators, then the system can have n number of natural frequencies. As a result, it can have n number of normal modes. Okay, so how do we derive an expression for these normal modes? We go to Fourier transforms. So this is how we do this. We are given this Hamiltonian over here. So using Hamilton's equations of motion, that is pi equal to qi dot equal to del h by del pi and pi dot equal to del h by del qi with a minus sign, I think, I can obtain the equations of motion from this Hamiltonian for the ith oscillator. So this is the equation of motion for the jth oscillator. M into uj double dot is equal to minus k uj minus 1 minus k uj minus uj plus 1. Okay, nearest neighbor coupling. So this is equal to k into uj minus 1 plus minus 2uj plus uj plus 1. This is the equation of motion for the jth oscillator, and j can go from 1 to n minus 1 with un and u0 fixed at 0. Okay, so now in order to calculate the normal modes, you see that an observation which you get over here is that the the oscillator J is coupled to its nearest neighbor oscillators. However, during the normal mode of oscillation, since all the oscillators oscillate in phase, in essence, they are uncoupled with each other, right? Because they are in phase. So basically, they are behaving like uncoupled oscillators in if they are oscillating in the normal mode. Okay, so you see that the normal modes of the system can be derived if I write, I'm able to diagonalize this matrix equation. Now, why do I call it a matrix equation? Well, because you have j going from 1 to n, so you can write 1 to n minus 1 equations over here. That becomes your column vector for the displacements at time t plus 1. For the derivatives of the displacement, that is the column vector. And on the right hand side, you can have the column vector of the displacements, which are uj's, and the column vector is pre-multiplied with a coefficient coupling matrix. And the coupling matrix basically contains elements along its diagonal. Why? Because there is only nearest neighbor coupling. Okay, so that is why it will be a diagonal matrix which will contain elements along the main diagonal and the diagonal above and the diagonal below. So yeah, so that will be the coupling matrix. So what I have to do now here is that I should now diagonalize the coupling matrix. So if I diagonalize the coupling matrix, then you will see the essentially the equation of motion which I get in terms of the new diagonalized coordinates, that is the new basis coordinates, you will see that they are uncoupled with each other. Okay, so how do I diagonalize this coefficient matrix, coupling matrix? What I do is that because the system has translational symmetry, I use Fourier modes. What are Fourier modes? Fourier modes are sines and cosines. Basically, so I can write the displacement in terms of sines and cosines instead of the now number u. So I can write uj and ua in a basis of sines and cosines. That's what I'm saying. Okay. So now since at the boundaries the particles are fixed, so the appropriate basis to be used is the basis of sines because sine vanishes at the boundaries. If I consider the boundary to be at 0 and 2 pi. Okay, so that is why I define the normal modes in this manner. So u tilde kn is the small nth normal mode. Okay, which has a wave vector whose angular frequency is small omega n and the wave vector is equal to kn. So ukn for the jth particle is given by root over of 2 by n e to the power plus minus I omega nt sine knj, where Kn is given by small n pi by capital N. So Kns are the wave vectors of the various normal modes of the system, and small n denotes the normal modes. N goes from 1 to n minus 1. So large values of n give wave vectors which are simply shifted by a multiple of pi, and hence they coincide with the above normal modes. So as I had mentioned earlier, so there are n minus 1 number of normal modes because there are n minus 1 number of moving elements in my system. Right. So why do I write un in this manner? Because the normal modes should also be orthonormal to each other. That is, if I do a summation from j equal to 1 to n minus 1, u tilde k n at j and u tilde k m at j, this is equal to delta nm. This directly follows from this expression. So basically, you have an integral of sine kx into sine ky, sine kx into sine mx dx, and you know that this integral is only non-zero if k and m are equal, otherwise they are zero. So that is how this Kronecker delta comes in. Okay, so now what I do is that I substitute the normal modes into this equation of motion. So basically, in place of uj, I put u tilde k n j, and similarly on the right hand side also I do the same. And then I use the formula for basically sine a minus sine b and sine a plus sine b. If I do that, then what you will see is that this equation of motion, it gives me omega n square equal to omega naught square into 1 minus cos n pi by 2n. This 2 won't be there. It will be, this 2 should not be there. And you know that if 1 minus cos n pi by 2n can be written as 2 sine square n pi by 2n. Right. So that is why this 2 should be actually be over here. So omega n square is equal to 2 times omega naught square sine square n pi by 2n. So I obtain the dispersion relation for the normal modes, right? Where omega naught equal to k by m. So once I get the angular frequency in terms of the omega naught, which is given in terms of the coupling, as well as the wave vectors k, then I can easily find the potential energy of the system, right? So then the potential energy turns out to be equal to this. Why this quantity? Because it should, sorry, there should be a 4 over here. Yeah, so potential energy turns out to be equal to this because potential energy should be half m omega square into amplitude square, right? So the I have, yes. So this is the omega square which I had over here. Half m omega square is the potential energy. This is the expression for the potential energy of the nth normal mode of the system. So now I can write the displacement of the jth particle in terms of the basis of normal modes, right? So express the Hamiltonian in terms of the amplitudes of the normal modes and evaluate the classical partition function. So in order to first express the Hamiltonian, we need to evaluate the potential energy first. The kinetic energy part does not matter because that is independent of the coordinates itself. So pi square stays only pi square. So we are concerned with the potential part, which consisted of the coupled quantities, right? So now first I express the displacement of the jth oscillator in the basis of the normal modes. So uj is equal to summation of small n equal to 1 to capital N minus 1 an u tilde k n j, where an is the amplitude of the nth normal mode. So then the expression for potential energy u is equal to k by 2 I summation I equal to 1 to n ui minus 1 whole square, which can, if I replace ui by the expression of uj which I have over here, then this becomes k by 2 summation I equal to 1 to capital N, and then again a summation over of n equal to 1 to capital N minus 1 an u tilde k n I minus u tilde k n at I minus 1 and the square of this quantity. Now we use the expression of orthonormality to simplify this even further. So since we know that summation, so basically if I do this thing, I get a number of cross terms. Okay. Terms like u tilde kn multiplied by u tilde km at j minus 1 and so on. So because of this orthonormality, this becomes equal to 1 by n delta nm into summation j equal to 1 to n minus 1 minus cos kn at 2j minus 1 plus cos kn. So this is nothing but delta nm cos kn. So if I expand this summation, I get all the cross terms, and then I use this quantity to simplify these cross terms, and then finally I would get the total potential energy to be summation of n equal to 1 to capital N minus 1 an square 1 minus cos kn, right? And k was what? N pi by capital N. So this is 1 minus cos n pi by capital N, and this can be written as 2 sine square n pi by 2 capital N, right? So that is why this can be written as 2k into summation I equal to 1 to n minus 1 a k n square. Basically a n square I'm writing as a k n square sine square small n pi by 2 capital N. So this is the form of the potential energy. And you see now that the potential energy is now decoupled when I write it in the basis of the normal modes, where AKs are the amplitudes of the normal modes. So earlier I had the potential energy consisted of various terms coupled to each other. Now when I express this in the basis of the normal modes, it becomes decoupled, and now it becomes easier for me to solve the Hamiltonian and simplify the system even further. So the total kinetic energy becomes total energy becomes equal to the this term, firstly the I equal to 1 to n minus 1 pi square by 2m plus summation 2k into summation I to 1 to n minus 1 akn square sine square n pi by 2n. So in the next step, what I do is that I calculate the partition function in terms of these new coordinates. Now, since this is a canonical transformation to the normal modes, the Jacobian associated with this transformation is unity. Therefore, the classical partition function can be written in the following manner. It can be written as the summation over all momenta and positions e to the power minus beta h cross. E to the power minus beta h. H is the Hamiltonian. So now I have summation over n number of momentum coordinates, n minus 1 number of momentum coordinates, and n minus 1 number of position coordinates, right? So since the momentum coordinates are basically independent of each other, I can write them in terms of 1 by lambda to the power of n minus 1, the entire integral over momentum, where lambda equal to h by 2 pi m kbt corresponds to the contribution to the partition function from each momentum coordinate. So each of them contribute the same amount over here. Okay. And then I have the integral over the position coordinates, which are minus to plus infinity dA1 dot 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 up to dAn minus 1 e to the power of minus 2 beta k summation n equal to 1 to capital N minus 1 an square sine square n pi by 2 capital N. Okay. So now you see that each of these integrals is basically a Gaussian integral. So I have to perform n number of Gaussian, n minus 1 number of Gaussian integrals. And if I do that, the partition function turns out to be this. So this is 1 by lambda into the lambda to the power n minus 1 pi kbt by 2k whole to the power of n minus 1 by 2, and then a product over n equal to 1 to capital N minus 1 sine n pi by 2n whole to the power of minus 1. Okay, so this directly comes if I do the Gaussian integrals over ans. So now I obtain my partition function for a chain of n coupled oscillators. So once I do that, so I was saying that this is a very important problem. It has also many interdisciplinary applications. Now, why was I saying that? Because the oscillator, the simple harmonic oscillator, to be even more simpler, it forms one of the simplest and basic forms of a dynamical system. And everything that one sees around in the world around oneself is a dynamical system. Basically, a dynamical system is something whose time evolution can be written as a function of its properties, features. For example, x dot equal to f of x. So this is a dynamical system where it describes the evolution of the quantity x in terms of a function of various other quantities which can depend on x itself. Okay, so the simple harmonic oscillator forms one of the most basic dynamical systems, right? And in order to model different kinds of phenomena, starting from neurons to climate and so on, simple harmonic oscillators can be used as the basic building blocks for these models. You use different simple harmonic oscillators, couple them in different ways, and you can observe different kinds of things. So this chain of coupled harmonic oscillator example, which I showed over here, is one simple model which you can form by coupling the oscillators in a line. Okay. You can also form many other more complex models for which the evaluation of normal modes may or may not be possible analytically. It was possible over here, it may not be possible for the other cases. All right. So that underlines the importance of studying problems like these. So the next question is that first I have to evaluate expectation of mod u tilde k square, and then I have to use the result to calculate expectation of ui square, and then I should plot the resulting square displacement of each particle as a function of its equilibrium position. Okay, so what was u I had earlier? U could be expressed in this form, right? So expectation of uj square is basically the expectation of this entire quantity whole square, right? And since UJs are the basis vectors, so expectation of UJ square is basically, sorry, expectation of UN tilde square is basically UN tilde square. That is why this turns out to be a summation over small n equal to 1 to capital N minus 1, expectation AN square into U tilde N square. So in order to evaluate expectation UJ square, I need to first find out expectation of AN square. So what is that? So expectation IN square is basically integral from minus infinity to plus infinity AN square into exponential of this potential part of the energy which I had earlier. Why does the kinetic part does not come up over here? Because it cancels out from the numerator and the denominator. That is why the kinetic energy part does not show up here. You have an integral from minus into plus infinity dAn an squared exponential of minus 2 beta k n squared into sine square n pi by 2n divided by the integral of the rest of the quantity. If I evaluate this, this turns out to be kbt by 4k 1 by sine squared small n pi by 2n. Okay, so then I get the expectation of uj square if I substitute the expression of an square over here. So this turns out to be equal to kbt by 2 capital Kn summation n equal to small n equal to 1 to capital N minus 1 sine square n pi j by capital N divided by sine square n pi by 2n. Yeah. Now I have to further evaluate this summation. So this evaluation of this summation is considerably simplified if I consider combinations like these. Okay. So if you consider combinations like these, this is equal to minus kbt by capital Kn, and then basically you obtain a in this way you obtain a recursive relation basically for uj's. So this is, if this is a relation between uj plus 1, uj minus 1 and uj, and if I use the fact boundary conditions that u0 square expectation and un square expectations are 0, then I can solve for the various displacement in terms of the recurrence relation, and the generic solution turns out to be expectation uj square is equal to kbt by capital K j into n minus j by n. So now it is said to me that I have to plot the square displacement of each particle as a function of its equilibrium position. So one thing to note is that if j is equal to 0 to 0, j equal to n is equal to 0. So how does this plot look like? This plot looks like this. This is the function, this is the plot of expectation of uj square. So expectation uj square is maximum at the midpoint of the chain, and it decreases on other sides. Okay, so how are the results modified now if I have only the first particle to be fixed while the other end is free? What changes in that case? So if the other end is free, then it becomes a much simpler problem because now I don't need to evaluate the normal modes again because the last particle is free. So I can write the partition function by simply changing the variables to the differences between the nearest neighbors. So why? Because when the last particle is free, then the potential energy of the spring can be written in this manner. So you basically had this generic form of the potential energy, which is the summation over all the pairs. Okay. And if only the first particle is fixed and the last one is free, then the potential energy basically turns out to be equal to k into summation j equal to 1 to n minus 1 uj minus 1 whole square by 2. This is the expression for the potential energy. And this potential energy is itself decoupled and can be written independently in terms of a set of new independent variables, which I define as uj, delta uj. So if I define delta uj as uj minus 1, then u basically becomes k into summation over delta uj squared by 2. As simple as that. So then I can express the partition function in terms of these new variables that are delta uj's. And then I can evaluate the partition function, which turns out to be 2 kbt by lambda square k whole to the power capital N minus 1 by 2. Right. Then for each spring extension, we have delta uj square expectation is basically this thing, which is equal to kbt by capital K. This can be obtained easily in the similar manner in which I had obtained an square. Okay. So then the displacement uj is equal to summation of I equal to 1 to j delta ui. This directly follows from that because u0 is fixed. So u0 minus u1 plus u1 minus u2 plus u2 minus u3. So the middle terms all cancel out and I finally get uj. That is how I can express the displacement. So this is a sum of independent random variables, right? Because delta u's are all independent random variables. So you see that the displacements are a sum of independent random variables. And if I do this summation, then I obtain this particular form of the variance, that is kbt by k into j. So you see that the variance of the amplitude increases like this if there is a free end. So the last oscillator has the largest amplitude, RMS amplitude, while the first oscillator is fixed if the ends are free. Okay, so that concludes the discussion for today's session. So I'll be sharing the recording on YouTube and I will meet you again next day.